In this video, we're going to be looking at a paper called Efficient Analysis of Large Adaptation Spaces in Self-Adaptive Systems Using Machine Learning. The goal of this paper is to show that a learning module implemented into a MAPE-K feedback adaptive system can reduce the adaptation space without noticeably affecting the performance of the application. So essentially this means that we're going to try and input a machine learning model into a adaptive system so that when it's looking at this massive adaptation space of changes that it can and cannot make to try and meet its goals, we'll be reducing the number of options you can choose from so that it can navigate through these options a lot faster and choose the better option. Now, this paper, they did it on two applications. They ran some experiments. The first one is a Delta Internet of Things.v1 and the second one is a .v2. Now, V1 is a security network on a campus. It has multiple nodes, and each node has sensors such as heat and motion detectors. Now, this returns all the data back to a controller end-use device across a network. This means that we have one device that kind of receives all of this data. And the adaptation space of this network is the things that the system can change is the power settings of the nodes, and then changing how the messages distribute across that network. .v2 is very similar, except that it's on a particular faculty block, which means that it's actually a lot larger than v1, which means that the adaptation space is considerably larger. So there's two approaches to creating this learning model, machine learning model within the learning module. They use classification and regression, and both of those are online algorithms, which means they update consistently throughout the lifetime of the program. So classification uses stochastic gradient descent, a linear version of this, to label each option in the adaptation space with a useful, not useful label. And then whatever data is labeled useful is looked at by the analyzer. And so it reduces the adaptation space quite a bit using this method. Regression uses a very similar method, except it tries to find values like real values, which uses optimized parameters. So rather than labeling each option, it simply tries to find the best options within the adaptation space. So how does it actually all work together? Well, down here at the bottom we have the managed system, which is the Delta V1 or V2, which is being run. Then we have a monitor, which simply monitors the managed system and makes sure everything's working. The analyzer takes information from the monitor and decides if the managed system is meeting the adaptation goals. If it's not, it will ask the machine learner to give it the adaptation space, a subset of the adaptation space, and the machine learner will go in here, it'll take the adaptation space, and then it'll squeeze it through this learning model, and out will get a subset of the adaptation space, which the machine learner thinks are the most efficient for the analyzer. The analyzer will then use a verifier to decide if which option from the subset to use, which will then go into the planner, the planner and the executor together will implement that change onto the system at the bottom here. This learning model will also be updated along this process, and so it'll keep up to date with all the concepts that are going on here. So if there is a concept drift, the learning model will stay up to date and will try and keep on top of it as best it can. So how do they actually evaluate this? Well, they ran both the Delta programs on simulated networks, and they had enough time to run several variations of the adaptation process. They found some very interesting results. They found that the learning module reduced the adaptation space on average for 50% with the V1 and 75.5% for V2. This is a considerable reduction of the adaptation space, but they also found that reducing the adaptation space didn't actually compromise their adaptation goals and reduce the time to run the self-adaptive by 55 to 76%, which is a huge amount, especially without compromising that adaptation goal. Essentially, this means that there's no drawbacks to using these learning models within the adaptive system. So in conclusion, the researchers found that using machine learning as a learner module within the self-adaptive process reduced the adaptation space dramatically, considerably decreased the runtime of the program, and finally did not compromise the optimization goals. So it seems that the paper was a huge success. There were several other directions that they said they would like to continue more study into. One of those was learning how to deal with more than just the two goals in the adaptation space, and so they would like to have many more goals and see how that would impact the models. They also said that they would like to try much more complicated versions of the machine learning models, such as deep learning and so on and so on. Awesome. Thank you for watching this video.